Well, when last we visited with Western world's chief physicists, we learned how things at the subatomic level have gotten first relative, thanks to Einstein, and then completely uncertain, thanks to Heisenberg. But everything's still okay, right? Reality is still reality at the macro level. We can trust it, can't we? Well, certainly Isaac Newton thought we could when that apple fell on his head. He didn't think anything was very weird about the law of gravity that he invented that day. It was really straightforward. The world is the world. All these events are happening against a static space and across the procession of a steady time. Nothing really weird about it. A meter's a meter, a second is a second, right? We'll see today how wrong Newton was. How time is actually relative, not steady. How space actually warps and is not just a static background. And believe it or not, how an apple is not really an apple at all. Reality really started falling apart with old Einstein and his theory of the relativity of time. It's captured by the famous twin paradox you probably heard. Two 20-year-old twins, one of them jumps into spacecraft and heads off into light travel space, comes back some years later, and the brother, who's now 60, not 20, is surprised to see that his sister is 40. Well, how the heck can that be? He, of course, just says, well, she just thinks she's 40. In reality, she's 60, just like I am. But Einstein says, no. In reality, she's 40, and you're 60, buddy. Her opinion is just as equally true as his. That's the facts of rapid travel through space and time. So to see how time slows with motion, let's use a frame here that we will all imagine is a photon clock. Now, a photon clock has photons bouncing back at the speed of light. Every time one bounces, it's a nanosecond or so. So boom, 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 3 seconds, 3 nanoseconds pass. But if the photon clock is passing through space, of course, the photons travel this diagonal path, from our point of view anyway, and therefore at the same speed they're going further and it takes longer. Very strange. So the time looks different from the stationary point of view than it does from the moving point of view. So time is indeed relative. Cope with that for a little bit, if you will. Don't worry, there's a happy ending. So, relativity, Einstein said, actually affects space just as much as it does time, right? Newton thought of space this way. There's an x-axis, there's a y-axis, there's a z-axis, just like in the 3D movies. But Einstein said, no, there's a fourth dimension. There's the time it takes that apple to fall and hit Newton in the head. So that's a really weird thing to get your head around. Einstein said, in fact, that everything travels through space-time at the speed of light. How can that be? Well, think about it. A photon is traveling through space-time at 176,000 miles a second. So a long way in a very short period of time. We, on the other hand, are crawling through space, relatively speaking. Time, sadly, is flying by, and soon we'll all be gone. So it's very strange at the macroeconomic level as well. One way to think about this, it's so hard to think about 4 dimensions, let's think about 2 or 3 dimensions instead, right? So let's say young Albert Einstein is traveling westward across the Bonneville Salt Flats in this 100-mile-an-hour vehicle. Takes him an hour, correct? However, late in the day, the sun's getting in his eyes, and he's kind of trying to sidle his way across without going blind, and things like that across the Salt Flats, and it takes him longer than that 1 hour at the same 100 miles an hour, right? So the same strip of desert, slightly sharing the velocity between 2 different dimensions, and it takes longer. And that's essentially what's happening with that 4th dimension of time. Although there's no way any of us can really think about this unless you're Einstein. So that's how time works in space-time, right? This is space-time. Here's where Newton's simple concept gets weird. Not that weird at the start, of course, right? It makes some sense that if space-time is a warpable surface like this, something with little mass does little to warp it. Something with bigger mass does quite a bit to warp it. So now we can think about what happened to Newton's apple in a whole different way. It was not being pulled by some invisible magical force, it was simply sliding down a crease in space-time, dragged by the Earth's warping of space-time. Same thing's happening with the Earth going around the sun, or any other gravitational effect. It's all caused by the warping of space-time. How warped is that? But then Einstein realized not just the unity of space and time, but the equation of energy and mass, of course, E equals mc squared, his famous equation. That's where it really gets weird, because this totally destroyed the idea that objects are made up of particles and energy of waves. It's now been just realized that energy and objects are both made up of something that is wave-like and particle-like at the same time. And eventually this led to Heisenberg's uncertainty principle, where you can't know a position and the speed at the same time. There's a corollary to that from Heisenberg, though. You can't really measure a particle's energy at a certain time because measuring it takes some time. So what that means is that this has been borne out by experiments, folks. It's true. There's now, the fact is known that quantum mechanics means that a particle can borrow energy from another particle. So that an electron beam or one of these cosmic rays coming down through lead, they pour through because they borrow energy for a split second or less and pay it back, but meanwhile they pass through the barrier. So that puts us in a weird position where at the subatomic level things are weird, even though they're more less likely to happen. But I could stand here clapping my hands and eventually they would pass through each other. Now it would take some time, probably about 12 billion years to guarantee that it happened. But hey, what's 12 billion years between friends? So what is reality? Well, basically it's kind of an absurdly unknowable thing. And this bothered Einstein to his death, of course. But we don't have to worry about it, we're not physicists. And as the great philosopher Bobby McFerrin said, simply don't worry, be happy.